Hello, my name is Jiwon Chong, and in this video, recorded for the Interspeech 2020, I will present our paper, Acoustic Scene Classification using audio tagging. So these are today's contents. I will first start with an introduction and motivation. Then, two baseline systems, each for acoustic scene classification and audio tagging, will be explained. In the next section, we use the audio tagging system to improve an ASC system. Experiments and corresponding results will be then presented, followed by a conclusion. Let's start with an introduction. An ASC system, acoustic scene classification system, performs multi-class classification like the image classification, except that it classifies acoustic scenes. Recent systems either compose an end-to-end DNA system or extract code representations using the DNN and exploit a different backend classifier such as an soft vector machine. However, because of the high intra-class variance, ASC is harder than it appears. Let's take a look at a shopping mall for an instance, which is one of the predefined acoustic scenes in the DK's challenge. Moving shopping carts will yield sounds similar to other vehicles like cars or buses. People talking, on the other hand, will contain different acoustic characteristics. An ASC system is difficult because it has to group these diverse acoustic characteristics into an identical class. While wondering how to improve an ASC system, we noticed that humans perceive an acoustic scene based on various sound events that they detect. For example, knowing that people are talking around and there are dishes and music sounds, one can easily infer that he or she might be in a cafe. The main objective of this study is to mimic this perception mechanism by using a pre-trained audio tagging system. An audio tagging finds out whether a group of predefined sound events exist in an input segment. In other words, it performs a multi-label binary classification. We propose to concatenate the output of an audio tagging system with an ASC system's code, or use it to derive an attention map for the ASC system. Looking at the below illustration, our study adds the blue box here. So this is for the concatenation, and this is for the attention that we will later explain. Now I move on to the baseline systems for the ASC and the audio tagging used in this study. The ASC baseline is a variant of discrete excitation ResNet. We extract mere spectrograms from the raw waveform, feed it to a ResNet to extract segment level embeddings, and then exploit a soft vector machine SVM to perform classification. Using an SVM performed slightly better in our experiments compared to the end-to-end approach, and it is also more general in case where an ensemble is performed, so it will be better for the DK's challenge. For the audio tagging system, we use that of Akiyama et al. Since it has won the DK's 2019 challenge task 2, and the codes are available through the GitHub. It has a two-phase training considering the dataset composition that includes both human-curated data and noisy data. As illustrated below, the system has common feature extraction network and uses a separate fully connected layers, each for the clean and the noisy labels. Now let's move on to the proposed framework, acoustic scene classification using audio tagging. We propose to use a tag vector for the ASC system. A tag vector refers to the output of a pre-trained and fixed audio tagging system. We propose two methods motivated by the human perception mechanism, which exploits the presence of various sound events to perform the scene classification. The first proposed method for using audio tag vectors is by simply concatenating it with the ASC system's code representation. A vanilla ASC system only uses the feature map to extract the code representation. In contrary, the proposed method concatenates extracted tag vectors from the same audio segment with the code representation of the ASC system. So when concatenating the tag vectors with the ASC system, we varied two configurations. The first was whether or not to perform feature transformation after concatenation. Performing transformation would project the ASC code and the tag vector into a new space, and not performing would simply make weighted sum of the ASC code and the tag vector to classify acoustic scenes. The other configuration that we considered was whether or not to transform the tag vector into another space before concatenation, and if we do so, how many layers would be adequate. We compared these two configurations throughout the experiments that are later explained. Next, we propose to apply attention to the ASC feature map using attention maps that are derived from tag vectors. The intuition here is to emphasize relatively useful elements using the tag vector. So when performing attention, we will apply it to the feature map just before the global plane. We assume that the proposed two methods using the tag vector could be complementary. Thus, we try to apply both at the same time. To do so, we first generate an attention map using the tag vector and apply it to the feature map before global plane. Then, we also concatenate the tag vector with the ASC system's code representation. We compared two strategies when applying both techniques. First, we tried using shared transform layers to the tag vector. So, as the illustration here, we use the tag vector, process it through a shared transform layers, and use it for attention map, and also use it for the code representation. When using separate transform layers, we use different layers. So these orange layers here are used to generate attention maps for the ASC feature map, and the gray box here is used to transform the tag vector, which will be later concatenated with the ASC representation. In our experiments, using shared transform layers was better. Now let's move on to the experiments and results. We used the DK's 2019 challenge test 1A dataset. It has a total duration of 40 hours. The official 4:1 configuration was used to split the dataset into train and test sets. For the pre-trained audio tagging system, we used the DK's 2019 test 2 dataset. It has a total duration of 90.5 hours, where 80 hours are from noisy labels. So these are the results. First, let's look at the results of various configurations regarding concatenation. The baseline is a vanilla ASC system without using a tag vector. Overall, all configurations have improved performance. Among various configurations, mere concatenation of the ASC code and the tag vector was to show the least improvement. Performing transformations after the concatenation was also effective, where different number of using different number of fully connected layers before the transformation brought further improvement. And we had 3 hidden layers, which performed the best. These are the results of applying multi-head attention using the tag vector. Like the concatenation, applying multi-head attention using the tag vector improved the performance of an ASC system. The amount of increase was even higher than concatenation. We diversified the number of heads and the number of transform layers for the attention map. And in most configurations, the performance was stable as long as there was at least one transform layer. Assuming that the both concatenation and multi-head can be complementary, we experimented applying both. Once again, performance was stable regardless of the number of heads or the number of transform layers. The table up here uses separate transform layers for concatenation, and the lower table is the result of using shared transform layers. Comparing the best performance of 2 configurations using shared transform layers showed slightly better performance than using separate layers. So this is the conclusion. In this presentation, we introduced the idea of using tag vectors, the output of a pre-trained audio tagging system, in order to improve the ASC system's performance. We propose to concatenate, apply multi-head attention, or both using the tag vector. And using all 3 proposed methods showed consistent performance improvement. Finally, we have 2 future works that are done after submitting this paper. First, we further improved the study by proposing to use the last hidden layer of an audio tagging system rather than the output, and modify the attention mechanism into dual attention. The results will be presented at this year's DK's workshop. The other study that we did was building a common pre-trained model by combining acoustic scene classification, audio tagging, and sound event detection. This work is currently submitted for the next year's ICASP, and preprints are available at Archive. This is the end. Thank you for listening.